Hello, my name is Christopher Johnson, and welcome to my video lab report on Lab 4, Oscillations. I will begin by giving a brief overview of the lab and explaining all related physics concepts. Next, I will explain how I observed and gathered data from the video via tracker software. Next, I will show how I built a computational model to predict the motion of the object in the video, and then compare the predicted motion to the observed motion, as well as observe the energy changes throughout. To conclude, I will answer the what does it mean questions. In this lab, we will be analyzing the motion of a spring mass system swinging in an arc while oscillating on a spring. We will observe the actual motion as well as predict the motion through a computational model. This will be useful for observing the energy changes throughout the oscillations, which will give us a better understanding of kinetic, gravitational potential energy, spring potential energy, and total energy. As has been a common theme throughout our labs, we will use Newton's second law to predict the motion of an object given the initial position and velocity. A difference is that this lab deals with the motion of a spring system, so we must also account for the spring force, which involves the stiffness, spring constant, and relaxed length of our spring. Also, we will be testing the energy principle to observe the energy changes throughout the motion and how although the amount of one specific energy may change, that energy is conserved and either created or destroyed throughout this entire process. To begin analyzing the data, I must first make some initializations. I set the length scale to 0.7 meters and the frame rate to 10.5 frames per second. I then set the start frame from when the mass is initially released. I then chose the origin of our coordinate system to be the attachment point and track the mass throughout using the same process we have in previous labs. After tracking the motion, the graphs on the right side of the screen looks like a sensible harmonic motion, so I will now transfer the x and y positions of our observations to Excel to create a spreadsheet for future comparison and evaluation. To begin our computational model in GlowScript, I must first collect some necessary information from our tracker data. We know to predict the motion we need in initial position and velocity, which we can obtain from the data table of tracker. The object started at an initial velocity of 0x0y0z as it began from rest, and the initial y position was negative 0.641 meters. For our prediction, we also need to know the mass, which is 0.402 kilograms. Also, we need to know the weight force, the spring constant, and relaxed length. We can obtain these from tracker. We know the formula for the period of oscillation for a spring is equal to this, and given this, we can rewrite the formula to solve for k, or the spring constant. After measuring the distances between oscillations in tracker, I found the average oscillation period to be 1.519 seconds. Using this data, we can now solve for our k. To find the relaxed length of the spring, we can simply note where the system is at equilibrium via tracker, which has already been noted at 0.7 meters. Because the system at 0.7 meters is in equilibrium, the sum of the spring force and the weight on the system is 0, so they must equal each other in magnitude. Writing this as a formula, we can rewrite the equation to solve for L0, or the relaxed length. We have all other data we need, including equilibrium and initial y coordinates. After calculating, the relaxed length of our system is 1.27 meters. We now have all necessary data to build a computational model. First, I input the data that we collected and calculated previously. In lines 48, 51, and 52, I set the ball's mass, initial position via tracker, and initial velocity, which was at rest. In lines 79, 82, and 85, I specify the force of gravity, the spring constant we just calculated, as well as the relaxed length we just calculated. We will now use the calculation loop to apply Newton's second law. We can do this by adding up the forces that are acting on the system and applying them to our system to find the new velocity. We calculate Fnet by adding the weight force and spring force together, and then using Fnet to solve for the velocity update formula, and then using the new velocity to update the position. Our calculation loop does this through every single time step. We are also interested in observing the change in specific energies, so we must first calculate the kinetic energy and both potential energies through every iteration. In lines 135 through 145, the formulas are moved into their code equivalent, and the changes in energy are also noted for each and every iteration. With all necessary motion and energy coded correctly inputted, we can now visualize our data to compare and evaluate the motion and energy changes of the system. After graphing our code, I'm able to make several observations about the data. First, to answer the what does it mean question, the energy principle is satisfied. Since the system is not moving, no work is being done, meaning energy should stay constant, which it does if you look at the orange line. As previously mentioned, gravitational and spring potential energy are inversely proportional through the observation period, but energy remains constant. Also, our observed and predicted observations are fairly similar. Any differences can be attributed to the intricacies of tracker or small detail issues when selecting the center of mass. To answer the what does it mean question 2, the oscillation period derived from the x position graph was approximately 1.66 seconds per oscillation. The oscillation period derived from the y position graph was approximately 1.5 seconds per oscillation. This difference would greatly change our results as the oscillation period is a factor when calculating the spring constant. To combat this, a different oscillation period can be made for both the x and y component of spring constant, or an average oscillation period can be taken.